Welcome back to the Deep Dive. Today, we're taking a look into the mind of a Nobel laureate, Vitaly Ginzburg. But maybe not in the way you'd expect.
Right. Usually you'd think, okay, Nobel Prize lecture, they'll focus on their biggest hit.
Right. Ginzburg won in 2003 for superconductivity and superfluidity theory.
Oh.
Huge stuff. You'd expect a lecture just on, say, the Ginzburg-Landau theory.
But he didn't do that. At 87, he chose a different path for his lecture. Quite unusual.
Totally. He spent a lot of time talking about unsolved problems, things we still don't know. And also this idea he called the physical minimum.
Which was like an essential knowledge kit for young physicists.
Yeah, like, here's what we've done, sure, but look at this vast ocean of stuff we haven't figured out yet. It's quite a statement.
It really is. It says so much about science itself. It's never really done.
So that's our mission for this deep dive. We'll follow his lead. We'll touch on his big achievements, of course, but really dig into those lingering questions, the roads less traveled in research, he pointed out, and that advice for physicists like you.
We're trying to get that unique perspective on how science actually happens. The breakthroughs, yeah, but also the human side, the debates, the stuff that gets overlooked.
And Ginzburg's phrase, the boundless sea of unresolved problems, we want to explore that. Plus, we're using his Nobel Lecture directly, so it's straight from the source.
A rare insight. Okay, so where do we start? His background.
Let's start there. He began his lecture expressing thanks, noting his age, 87, and his atheism, making living recognition especially valuable to him.
Right. But he quickly shifted focus to his influences.
His real teachers, he called them. Igor Tamm and especially Lev Landau.
And the Landau story is incredible. He was actually imprisoned, wasn't he, in 1938 to 39?
Yeah, it's quite chilling. And he only got out because Pyotr Kapitsa, another giant, basically vouched for him personally.
Imagine that.
Yeah.
And after that ordeal, Landau develops his theory of superfluidity. It shows incredible resilience.
Absolutely. And it shaped Ginzburg's perspective. He said he wanted to talk about what was and what was not done, not just rehash things everyone already knew, like the Ginzburg-Landau theory.
Which he preferred to call the psi theory, right? To avoid sounding.
The pretentious, yeah.
Yeah.
Which is pretty humble for a Nobel laureate talking about his most famous work.
It really is. So that psi theory, what's the core idea for, students listening?
It basically applies Landau's general theory of phase transitions, how things change state, like water to ice, specifically to superconductivity.
Okay. And it uses that order parameter, psi.
Right. Psi is this complex mathematical function, a scalar one, that kind of measures how ordered the superconducting state is, like how much the electrons are acting collectively.
And it links that psi to the electromagnetic field around it using the vector potential, A.
Exactly. And its phenomenological meaning, it describes what happens really well, even if at the time they didn't fully grasp the deep microscopic why.
It worked beautifully based on observations, which brings us to that debate he mentioned.
Ah, yes, the very interesting and intriguing one he had with Landau about the effective charge, E, in their own theory.
This is such a great story about how science actually works, disagreements and all.
So Ginzburg thought this E might not be the same as the basic electron charge, E?
Yeah, he suspected it could be different. He even looked at experiments and figured E was maybe 2 or 3 times E.
But Landau disagreed.
Initially, yes. Landau argued there were no grounds for it to be different. And he had a serious theoretical objection too, right, about gauge invariance.
Right. Could you maybe quickly explain what gauge invariance means here, just basically?
Sure. Fundamentally, gauge invariance means that the physics you can actually measure, the real-world outcomes, shouldn't change, even if you make certain mathematical adjustments to how you describe the underlying fields, like the electromagnetic potential.
Okay, so it's a kind of consistency check in the math.
Exactly. Landau worried that if E wasn't constant, if it varied in space, it might break this fundamental principle, leading to, well, nonsensical results.
So a real theoretical roadblock. How did they get past it?
The breakthrough actually came from outside their specific debate. It came in 1957 with the BCS theory, Bardeen, Cooper, and Schrieffer.
Ah, the microscopic theory of superconductivity.
Precisely. BCS theory explained that superconductivity happens because electrons form pairs, Cooper pairs. And these pairs act like single particles, Bose particles, in fact.
And crucially, what's the charge of a Cooper pair?
It's exactly 2e, 2 electrons pairing up.
So twice the electron charge.
Right. And then later, another physicist, Gorkov, actually derived the Ginzburg-Landau equations from the microscopic BCS theory. And guess what?
It showed E is 2E.
Exactly. It confirmed E equals 2E. So Ginzburg had this great reflection on it. He said, basically, Landau was right that E should be universal, and I was right that it's not equal to E.
Huh. So they were both sort of right, but missed the simple connection.
Yeah. The simple idea that E could be universally 2E just didn't occur to them at the time. He called it a classic case of blindness in science.
Wow. That's such a valuable lesson for anyone in science, especially students. Even the absolute top minds can admit something that seems obvious later.
Absolutely. It shows you need to be open to completely new frameworks like BCS that can shift your whole perspective. You can't just assume your intuition covers everything.
It's a reminder to constantly question assumptions. So despite that early puzzle, the Ginzburg-Landau theory was a huge success, particularly for what are called type I superconductors.
Yes, very successful there. Those are materials where the boundary energy between the superconducting and normal state is positive. And Landau also had early ideas about type 2 superconductors, which behave differently and became very important later.
Okay, so we've seen a key piece of his established work and the debates around it. But the really striking thing in his lecture was the turn towards the unsolved.
He really pivoted, didn't he? He highlighted things he felt were uninvestigated.
Like thermoelectric effects in superconductors? Sounds niche, maybe, but he clearly thought it was important.
He did. And there's history here. Back in 1927, Meissner had concluded that these effects where temperature differences cause currents or vice versa just don't happen in superconductors. Full stop.
And that was the accepted view for a long time.
For decades, yeah. But Ginzburg, way back in 1944, showed this was actually wrong.
How so? How could the effect be there if Meissner couldn't see it?
It's subtle. Ginzburg used the two-liquid model. You have to think of both normal electrons carrying current Jn and superconducting electrons carrying current Js.
Okay, two types of current flowing.
Right. And Ginzburg realized that if you put a temperature gradient across a uniform superconductor, a normal current Jn does start to flow because of the heat difference.
But you don't see it.
No, because immediately a superconducting current Js flows in the opposite direction and cancels it out perfectly. Net current, 0. It's hidden.
Ah, perfect compensation. Very clever. But are there situations where it isn't perfectly canceled, where you could see it?
Exactly. That was Ginzburg's point. He said if the superconductor isn't uniform, or if it's anisotropic, meaning its properties depend on direction, then the cancellation isn't perfect.
And then you'd get what?
You could get an observable thermoelectric magnetic field. He gave examples like a bimetallic superconducting loop with a temperature difference across the junction.
Or an anisotropic crystal.
Yes, like a non-cubic crystal. If the temperature gradient isn't aligned with the symmetry axis, you should get a magnetic field popping out perpendicular to the main current flow.
And these effects, measurable with modern tech, are still largely unverified.
That's what Ginzburg lamented. He was clearly frustrated. He put it down partly to the force of fashion in science. People just moved on to other topics, maybe flashier ones.
That's kind of amazing. A potential discovery predicted by Ginzburg, just sitting there, maybe waiting for someone, maybe one of you listening, to actually go and measure it.
It's a real possibility. Low-hanging fruit, perhaps.
Speaking of fashion in science, let's shift to high-temperature superconductors, HTSE. That field definitely had its moments of being in and out of fashion.
Oh, absolutely. Before HTSE, remember, critical temperatures, TC, were incredibly low. Mercury was 4.15 Kelvin. Everything needed liquid helium, which is expensive and difficult. Low-temp physics was very specialized.
And the existing theory, BCS theory, seemed to suggest there was a limit, right, related to the lattice vibrations.
Yeah, the BCS formula for TSC involved the Debye temperature linked to those vibrations. For most metals, that capped predicted TCs around maybe 25 Kelvin, 30 Kelvin max, matched what people saw.
So how do people even start thinking about radically higher TECs, like near room temperature?
Well, the big idea came from Little in 1964. He suggested replacing the phonons, the lattice vibrations, mediating the electron pairing in BCS with something else. Excitants.
Excitants. Those are electronic excitations.
Right. And the key is characteristic excitant temperatures can be way higher, like 10,000 Kelvin or more. If that worked, Little calculated you could potentially get TCs up to maybe 1,000 Kelvin.
Wow. That's a huge leap. Did Ginzburg jump on that?
Immediately. He proposed a different structure, a quasi-two-dimensional sandwich of conducting and insulating layers. He thought that would be more stable against fluctuations than Little's original one-dimensional idea.
But wasn't there a big worry that materials needed for such high TCCs would just fall apart? The crystal stability issue?
That was a major concern, yes. But Ginzburg, working with Kirchnitz, tackled that theoretically. In their 1977 book, they showed the lattice could actually be stable even under conditions needed for strong electron attraction.
So they basically removed that theoretical roadblock.
They did. And incredibly, their work predicted TCs up to 300 Kelvin room temperature were theoretically possible. This was almost a decade before the first HTSC materials were discovered experimentally.
That's stunning foresight. So theory was pointing the way, but what happened next? Did people rush to make these materials?
Well, no. Ginzburg actually notes that by 1984, HTSC research had become unfashionable. Again, the fashion factor. Until 1986-87, with the discovery of the cuprate superconductors, TC jumped above 77 Kelvin, the boiling point of liquid nitrogen. Suddenly, it wasn't just liquid helium anymore. Much cheaper. Easier.
And then the boom happened.
Ginzburg called it a boom and even a psychosis. Everyone piled in. It completely changed the landscape.
But he suggests the actual discovery of those specific cuprate materials was, well, a bit lucky, accidental.
He does imply that. While the general theoretical ideas of layered structures existed, nobody specifically said, go look at these copper oxide materials.
And he mentions that near miss in Moscow.
Yeah, a really poignant story. In 1979, researchers there made a ceramic, Le 1.8 SR 0.2 CuO4, very close chemically to one of the first big HTSCs.
They didn't cool it down far enough.
Exactly. They only measured resistance down to liquid nitrogen temperature, 77 K. The superconductivity kicked in just below that. They missed it.
Oh, brutal. But Ginzburg used this as inspiration, right?
Absolutely. His point was powerful. Even today, it is possible to make a major discovery and next year be awarded a Nobel Prize for it without gigantic facilities and the work of a large group.
He's saying you, students listening, you don't necessarily need CERN-level budgets. A clever idea, careful work in a smaller lab. It can still lead to huge things.
It's incredibly encouraging. Keep your eyes open, explore things others might overlook.
So even with HTSC discovered, are there still big open questions?
Oh, definitely. The exact mechanism driving superconductivity in the cuprates is still debated, surprisingly. And whether that excitonic mechanism Ginzburg was interested in plays a role, or if it's needed for eventual room temperature superconductivity, RTSC, still unclear. He certainly hoped RTSC would come via excitance.
Okay, let's touch on superfluidity. Ginzburg had that nice analogy.
Yeah, superconductivity is the superfluidity of a charged liquid, or superfluidity is the superconductivity of a non-charged liquid. Connects them beautifully.
And similar to the thermoelectric effects, he mentioned an analogous effect in superfluid helium-2.
The thermomechanical circulation effect. Again, predicted by analogy with superconductivity. Later observed, but then mostly ignored. Same pattern.
Another potentially rich area left unexplored. He also talked about a psi theory for superfluidity itself.
Yes, developed with Podevsky. Very similar logic to the Ginzburg-Landau theory for superconductors, same psi-order parameter idea, but for a neutral liquid like helium-2.
With a key difference at the boundary.
Right, the boundary condition is that the superfluid density goes to 0 right at the container wall.
But it had limitations for helium-2.
Big ones, quantitatively. Near the lambda point, the temperature where helium becomes superfluid, there are huge fluctuations. The basic mean field psi theory only works really, really close to p lambda, like within 1,000th of a degree.
Not very practical for describing most superfluid behavior, that.
Not really. So he and Sabyanin developed a generalized psi theory, trying to account for these fluctuations better.
And did that catch on?
Sadly, no. Ginzburg explicitly stated it had not come to the attention of either experimenters or theorists. But he still believed it had potential, that it can still yield much.
It's a recurring theme, isn't it? These potentially powerful ideas that somehow fell by the wayside.
It really makes you wonder what else is out there, maybe in old papers, waiting to be rediscovered or properly tested.
Which leads perfectly into the final, maybe most direct piece of advice in his lecture. The physical minimum.
This was his answer to a problem he saw clearly. Physics had gotten so huge, so specialized.
He worried about hyperspecialization.
He did. He said he was startled and dispirited, meeting young physicists who knew their tiny corner incredibly well, but had almost no idea about the big picture, the major questions across the field.
So the physical minimum was his proposed solution.
Exactly. A list, not of everything, but of the top problems of the day that he felt every physicist should have at least a basic grasp of, regardless of their specialty.
Like an update to Landau's old theoretical minimum idea from the 30s.
Precisely. And he stressed, look, this list is subjective, it'll change over time, it's not exhaustive. But the point is to broaden your horizons, give you a mental map of the whole landscape.
To help you see connections, maybe?
Mm-hmm.
Avoid getting stuck in just one silo.
That's the core idea. Innovation often happens at the boundaries between fields. If you don't even know what the other fields are, how can you spot those connections? It's about seeing the whole boundless sea he talked about.
So what kind of things were on his list around 2003? It must have been broad.
Incredibly broad. His 30-item list had things like controlled fusion, HTSC, and RTSC, of course, but also metallic hydrogen, quantum wells, quantum dots, Bose-Einstein condensation in gases, fullerenes, nanotubes.
So condensed matter, atomic physics.
Yep. Then nonlinear physics, turbulence, chaos, solitons. Particle physics, quarks, gluons, quantum chromodynamics, the Standard Model, proton decay, neutrino mass.
And astrophysics and cosmology, too.
Big time. Gravitational waves, the cosmological problem inflation, dark matter, dark energy, black holes, neutron stars, neutrino physics and astronomy, gamma ray bursts.
Wow. That's a lot.
Hey.
We didn't expect expertise in all of them, just a superficial idea.
Just enough to know what the questions are, why they're important, the basic concepts. He noted how the list changes. Quarks weren't on early lists, then became central. Fullerenes appeared. Gamma bursts became a huge topic.
It reflects the dynamism of physics.
Yeah.
He also highlighted 3 great problems, didn't he?
Yes, beyond the list, he singled out the arrow of time and entropy increase, the interpretation of quantum mechanics, what does it mean, and the origin of life from a physics perspective. Deep, fundamental questions.
These aren't just about solving equations. They're about understanding reality at its deepest level.
Absolutely. And this whole approach, focusing on the open questions, the big picture,
Yeah.
it all leads to his powerful conclusion.
Which was a direct counter to the idea that physics might be nearly finished.
Exactly. He knew some people thought, back around 1900 and even later, that we basically had it figured out, just needed to tidy up the details, the cloudlets.
But Ginzburg said,
He said, the entire history of physics, as well as the state of present-day physics and in particular astrophysics, testifies to the opposite. In my view, we are facing a boundless sea of unresolved problems.
what a message. So Vitaly Ginzburg uses his Nobel moment not just to look back, but to point forward emphatically.
He shows us science in action, the teamwork, the arguments, the moments you miss something obvious, the way fields go in and out of fashion, the lucky break. That's all very human.
And that physical minimum? It's a call for breadth. Know your field, yes, but know the field too. That's where innovation lies.
And that boundless sea, it's not daunting, it's an invitation, especially for you, the listeners interested in physics.
An invitation to dive in? His story shows massive discoveries are still possible, maybe in unexpected places, maybe by connecting dots others haven't seen. You don't always need the biggest machine, you need curiosity and breadth.
So let's leave you with this thought. If Ginzburg, one of the great minds of the 20th century, saw a boundless sea of unresolved problems as we entered the 21st,
what incredible, currently unimaginable shores might you discover in that sea? What will the next generation of physicists like you bring to light?